Hi, I'm Maurice Dupre, and in this section we're going to discuss the mean value theorem. The mean value theorem is one of the real workhorses of theoretical calculus. Much of the theory actually depends on the mean value theorem in various ways. Let's look at it. In order to begin, we consider a special case of the mean value theorem, which is known as Rolle's theorem. Suppose that y equal f of x is continuous at every point of the closed interval a comma b and differentiable at every point of its interior, the open interval a comma b. If f of a equals f of b, then there is at least one number c in the open interval ab at which f prime at c equals 0. And it's very important that this point c can be chosen to be in the open interval ab, that is strictly between the numbers a and b. Well, let's take a look and see what the situation is. We can actually realize this result very easily. If I have the graph of a function which has the same height at both endpoints of its domain, then since it's continuous, it's either constant, a straight line going across, or it could go up and then back down, or it could go down a bit and then up, or it might go down and up and wobble back and forth a few times. In any case, notice that if f of a equals f of b, it's either constant, in which case we can take for c any number we like in the open interval ab, or it's got critical points, because why? We know from our extreme value theorem that a function defined on a closed interval ab and continuous on that closed interval must have a maximum and a minimum value. And notice, if the minimum values happen at the endpoints, then the maximum has to happen in the interior if it's not constant. Or if the maximum happens at the endpoints, then the minimum has to happen in the interior if it's not constant. And if neither of the endpoints are max or mins, then of course we've got plenty of points inside, at least two, where the function will have to have a critical point, and since it's differentiable at every point in the interior, that critical point will be a point where the derivative is 0. And so that's Rolle's theorem. Now, one consequence of Rolle's theorem, which is very interesting, is the fact that if I have two functions, both of them continuous on the closed interval a comma b, and both differentiable on the open interval ab, with f of a equal g of a and f of b equals g of b, then f prime at c equals g prime at c for some c in the open interval ab. That is, notice what this is saying. The values of the functions at the endpoints are the same. That is, f and g have the same value at x equal a, f and g have the same value at x equal b. So if I draw their graphs, let's say there's a point on the graph where f passes through and g passes through at x equal a, and over here is the one for b. So let's say here's f and here's g. Notice I can find points here where the tangents are parallel, and that means f prime at c equals g prime at c. Now, why should this be true? Well, just consider the difference, f minus g. What happens if I plug in a into f minus g? Well, I get f of a minus g of a. The two are equal, so f of a minus g of a is 0. If I plug in b into f minus g, I get f of b minus g of b, which is 0, since f of b equals g of b. And so this vanishes at the endpoints of this interval. Well, in particular, that means this function f minus g has the value 0 at a and the value 0 at b. And so by Rolle's theorem, since the value at both endpoints is 0, the same number, and since the difference will be continuous, since f and g are continuous, and the difference will be differentiable on the open interval ab, since f and g are differentiable, Rolle's theorem tells me there's some point c in the open interval ab for which the derivative of f minus g equals 0. That is f prime minus g prime at c equals 0, or f prime at c equals g prime at c. It's a very simple, nice result. Now let's look at the mean value theorem itself. It's an easy consequence of what we've observed so far. Suppose y equal f of x is continuous on a closed interval a comma b and differentiable on the interval's interior a comma b. Then there is at least one point c in the open interval ab at which f of b minus f of a divided by b minus a equals f prime at c. Well, the equation looks complicated at first, but hold on a minute. Notice that if I have any curve given by the graph of a function on the closed interval ab, f of b minus f of a is the rise, the net rise, as we change x from a to b. So in other words, all we've got here is the rise over the run between the points a comma f of a and the points b comma f of b. So that would be delta y over delta x. So think of this as delta y over delta x. And so what does that mean? It's simply the slope of the straight line connecting the two endpoints of the graph. Well, now notice a straight line is certainly a nice differentiable function. It's certainly continuous on the whole interval AB, closed interval AB, and it's certainly differentiable in the interior because, in fact, it gives a differentiable function on the whole real line. So consequently, by what I just observed, notice the straight line is having the same value at the endpoints as the original function. So what we just observed shows that there have to be points in the interior where the derivative of the straight line function equals the derivative of the function f. You can see here in the picture there are three of them. Well, notice the derivative of the straight line function is the slope of the line, which is the delta y over delta x, or f of b minus f of a divided by b minus a. So consequently, as a simple consequence of Rolle's theorem, we have the mean value theorem. Well, right away, the mean value theorem has two important corollaries. Let's look to see what they are. Corollary 1. If f prime of x equals 0 at each point x of an open interval a comma b, then f of x equals a constant c for all x in ab. That is, f of x equals c for all x in a comma b, where c is a constant. In other words, the only way a function can have zero derivative on an interval is to be constant on that interval. Notice, whenever you differentiate a constant, we know we get 0, and so what this is telling us is that's the only way to get 0 when you differentiate a function differentiable on an interval. Now, how is this a consequence of the mean value theorem? Well, suppose the function's not constant. That is, suppose there are 2 points on the graph of different height. So well, by the mean value theorem, there has to be a point in the interior where the tangent line has the exact same slope as the line connecting those 2 points, at least one. But notice if the two endpoints don't have the same height, the slope of that line is not 0. And that would contradict the fact that f prime of x equals 0 at each point in the open interval a comma b. So remember then, for a function on an interval, the only way its derivative can be 0 is for it to actually be constant. Another result that is an immediate consequence of that corollary is if two functions have the same derivative at each point in the open interval a, b, then there exists a constant capital C such that f of x equals g of x plus c for all x in the open interval a comma b. That is, f minus g is constant. That is, think of it this way. If f prime of x and g prime of x are equal, that is, if f and g have the same derivative, then f minus g has derivative equal to 0, and so f minus g is constant by the previous corollary. Now, you have to keep in mind that we're assuming here that the function is differentiable at each point of the interior of this open interval. If that is not the case, if there's any single point where either of those functions is not differentiable, then the hypothesis would be violated, and in fact you could find counterexamples. Well, let's look at a problem testing our knowledge of Rolle's theorem. The function f of x equals x for 0 less than or equal to x less than 1, but f of x equals 0 when x equals 1. Notice it's 0 at x equals 0 and x equals 1, and differentiable on the whole open interval 0, 1, but its derivative on 0, 1 is never 0. In fact, notice if I differentiate the function f of x equal x at any point in the interior of the open interval 0, 1, I simply get 1. Certainly not 0. How can this be? Doesn't Rolle's theorem say the derivative has to be 0 somewhere in 0, 1? Well, no. Because Rolle's theorem also says in order to have that conclusion, the function, besides being differentiable in the open interval, must be continuous on the whole closed interval. If this function were continuous on the whole closed interval, then its value at 1 would have to equal the left-hand limit as x approaches 1, which would be the limit of x as x approaches 1, and that would be 1, not 0. And so consequently, the only way this function can be continuous and have this expression valid for x between 0 and 1 is in fact for this expression to be valid on the entire closed interval 0, 1, and certainly that's not the case for the way we've defined it here. One useful way to use the mean value theorem or even Rolle's theorem is in applications where we want to see how many times a function's graph crosses the x-axis, that is, solving f of x equals 0. You know, many times we're interested in solving polynomial equations of the form f of x equals 0, where f is a polynomial function, and Rolle's theorem and the mean value theorem can often help us out. Let's look at an example. Show that if f double prime is greater than 0 throughout an interval, closed interval a comma b, then f prime has at most one 0 in the closed interval a comma b. What if f double prime is less than 0 throughout the closed interval a b instead? Well, let's take care of both of these at the same time by just assuming that f double prime is not equal to 0 on the whole interval a comma b. Notice if f prime double prime is not equal to 0 on the whole closed interval a b, you might remember there's a theorem called Darbo's theorem which says any derivative has to have the intermediate value property. So if f double prime were negative somewhere on this interval and positive somewhere else on this interval, then Darbo's theorem would tell us, in fact, it was 0 at some point in that interval, which would violate the assumption. So in fact, this assumption tells us that either it's positive throughout the interval or it's negative throughout the interval. So consequently, given that it's non-zero throughout the interval, suppose f prime has two zeros. So f prime at C1 equals 0 equals f prime at C2, with C1, C2 in the closed interval AB. Well, now we can apply the mean value theorem, or in particular Rolle's theorem, to the function f defined on the closed interval C1 comma C2 in case C1 is less than C2. And of course, we can assume our notation here is that C1 is less than C2. So we'll just C1 less than C2. On that closed interval, f prime vanishes at the left endpoint, f prime vanishes at the right endpoint, and so Rolle's theorem tells us at some point inside that interval that some c in C1 comma C2, in fact, in the interior of that interval, we have the derivative of f prime, and that's the second derivative, equals 0. And that's what we call a contradiction of our assumption that f double prime is not equal to 0 throughout the closed interval. So there, as a result of Rolle's theorem, we see that if the second derivative is non-zero throughout a closed interval, then the derivative can have at most 1 0. Let's see how we can use Rolle's theorem to analyze the roots of a polynomial. Show f of x equal x to the fourth plus 3x plus 1 has exactly 1 0 in -2 comma -1. Of course, f of x being a polynomial is continuous on the entire real line and differentiable. In fact, it's differentiable as many times as you want to differentiate. And so consequently, we can certainly apply Rolle's theorem or the intermediate value theorem, and we can apply the mean value theorem. To start, let's look at what the value is at -2. Well, we have -2 to the fourth power plus 3 times -2 plus 1. And -2 to the fourth power would be 16. 3 times -2 is -6 plus 1. So we have 16 minus 6 is 10 plus 1 is 11. How about the value at -1? F of -1 is -1 to the fourth power plus 3 times -1 plus 1, which is 1 minus 3 plus 1. That's 2 minus 3 is -1. So now what we've found is at the one end point, -2, the function takes a positive value. At the right end point, -1, the function is taking a negative value. And so by the intermediate value property of continuous functions, we know this function has at least 1 0 in that interval. So we have at least one place where the graph crosses the x-axis. But suppose there were two. So here's -2, -1. If the graph did this, or it did this, or both, whatever, we see by Rolle's theorem, there's a point inside that interval at which the derivative is 0. So now let's look at the derivative and see where can it be 0. So we differentiate the function. F prime of x is 4x cubed plus 3. So to find where it can be 0, we simply set the expression equal to 0 and solve for x. So what we find is x cubed is -3/4. And consequently, x itself, where the derivative is 0, has to be -cube root of 3/4. Well, the cube root of 3/4 itself is a number between 0 and 1, so its negative is between -1 and 0. That is bigger than -1. It can't be in that interval. That is, what we've discovered is that the only place where this function's derivative is 0 is outside this interval. And so Rolle's theorem now tells us there can't be any two places where the graph crosses inside that interval. If there were, there'd be a place inside the interval where the derivative is 0, but there isn't. Let's look at a problem where we use Rolle's theorem to analyze the roots of a function. Show g of t equals square root t plus square root of the quantity t plus 1 minus 4 has exactly one root in the open interval 0, infinity. In fact, we'll show it has exactly one root in the closed interval on 0 all the way out to infinity. That is, notice the function's domain is all numbers t greater than or equal to 0. And so consequently, I'm going to begin by looking at the value at 0. G of 0 is square root 0, 0, which is 0, plus square root of 0 plus 1, that's just 1, minus 4 is -3, and that's, of course, less than 0. How about for big T? Well, notice for T very big, the square root of T is going to infinity, and so that'll totally overpower the -4. And for big T, G is positive. Certainly, G has plenty of positive values, and in fact, if I take T to be 16, the square root of 16 being 4, the first term will cancel that, and then we'll end up with square root 17. That is, G of 16 equals square root 17, which is certainly positive. So now, if I look at the interval 0 to 16, I have a negative value at the left endpoint, a positive value at the right endpoint, and so somewhere in between we have to have a crossing of the horizontal axis. That will be a root inside the closed interval 0 to 16. Now, notice that since the value at 0 is negative, that root can't be at 0, so it will be in the open interval 0 to infinity. So we have found that there is a root in the interval 0, 16, the open interval. How do we know that? Well, at the endpoints, we're not 0, but there has to be a 0 in between by the intermediate value property for continuous functions. Now, on the other hand, at this point, for all we know, there are plenty of zeros, and there might be other zeros beyond the 16. And so, in order to analyze that, we use Rolle's theorem. We take the derivative. G prime at t equals, well, the derivative of square root t is 1 over 2 square root t, plus the derivative of square root of the quantity t plus 1 is 1 over 2 times the square root t plus 1. And of course, the derivative of the -4 is 0. So there's our derivative. And notice that as long as t is positive, which is the only place that that term will make sense, on the entire interval from 0 to infinity, that is a positive number. If there were two roots, Rolle's theorem would tell us that at some place between those two roots, the derivative would have to be equal to 0. Since our derivative is always positive, Rolle's theorem is now telling us there cannot be more than one root. Since we know there's at least one root in the interval 0 to 16, we've now seen that there is exactly one root in the entire domain of this function. Remember, one of the corollaries of the mean value theorem says that if two functions have the same derivative on an interval, then they can only differ by a constant. This allows us to determine a function when we know its derivative and a single value of the function. Let's look and see how this is done. find f with f prime of x equal 2x minus 1, and whose graph passes through the point with coordinates 0, 0. Well, if the graph passes through the point with coordinates 0, 0, that's telling us f of 0 equals 0. So we've got a particular value of the function at a particular point. Now let's look at the derivative. F prime of x equals 2x minus 1. Can we think of a function whose derivative is 2x? Certainly x squared comes to mind right away. X squared prime, the derivative of x squared, is 2x. Can we think of a function whose derivative is 1? Well, that's even easier. The derivative of x is 1. So the difference rule for derivatives tells us the derivative of x squared minus x will be 2x minus 1. If I differentiate x squared minus x, I get 2x minus 1. So now we're close. X squared minus x can only differ from our function by a constant, because x squared minus x and f of x, notice they have the same derivative, 2x minus 1. So let's write f of x equals x squared minus x plus a constant c. So now we merely have to figure out what can the capital C possibly be. To do that, we come back to our condition that we have from the graph passing through the origin, namely f of 0 equals 0. So let's plug that in. 0 equals f of 0 equals 0 squared minus 0 plus capital C. And that's just the capital C. So follow this back. The capital C has to be 0. And so that means, in fact, our function must be simply f of x equals x squared minus x. Let's look at a problem involving what's called the geometric mean of two numbers. The geometric mean of two positive numbers, a and b, is the number square root of their product, ab. In other words, when I take the square root of the product of two numbers, we call that the geometric mean. Notice it's the multiplicative analog of what you do to average two numbers, which is with summation, you add and divide by 2. Show that the value of c in the conclusion of the mean value theorem for f of x equal 1 over x on an interval of positive numbers a comma b is c equals the geometric mean of a and b, the square root of ab. Okay, so remember the mean value theorem says that the net rate of change from one end to the other, the rate of change, is equal to the derivative at some point in the interior. So let's differentiate our function. F of x equal 1 over x has derivative f prime of x equals negative 1 over x squared. So that means our expression for f prime at c here is going to be negative 1 over c squared. On the other hand, let's compute exactly what the rate of change is over that whole closed interval. That's f of b minus f of a divided by b minus a, which in this case is simply 1 over b minus 1 over a divided by b minus a. In the numerator here, let's get common denominators by cross multiplying. So we'll have a minus b divided by ab all over b minus a. Notice a minus b divided by b minus a is simply negative 1, and so we end up with negative 1 divided by ab. So the mean value theorem tells us that this net rate of change over the whole interval a comma b has to be equal to the derivative f prime at c for some c inside the open interval a comma b. That means at some point c we have equality between these two expressions. Well, notice what that'll mean. The numerators are the same, so the denominators have to be the same. That is c squared equals ab. Well, that means c is the square root of ab. Well, we've looked at Rolle's theorem and the mean value theorem. We've seen how they're actually easy consequences of the extreme value property for continuous functions, together with the fact that extreme values have to occur at critical points for functions, and critical points for differentiable functions mean points where the derivative is zero. We've seen that two differentiable functions which have the same derivative on an interval can only differ by a constant, and that's a very useful fact for finding functions when their derivatives are known. We've also seen that the mean value theorem and Rolle's theorem can be used to analyze roots of functions. Keep in mind that when you do this, the intermediate value property is generally useful to see that you have at least one root by finding a negative value and a positive value. Well, now that you've seen these problems worked, you might want to try some on your own.